So John Begg, who's a geologist from GNS Science and is in charge of geographical modelling, is going to go first, because this will give you the best perspective on what is actually happening in the aquifer. Its makeup, its layout, all those things. Then we'll go to Dr. Jeff Smith from the Regional Council, and then Uwe will have you last, where we'll talk about the new water. All right? Yeah. Okay. Cool. Okay, John.
Thanks very much, Lawrence. I think you might have set the bar pretty high. What I wanted to say is what we think is beneath the Heretaunga Plains. So let's just start off from that point. So if we take the next slide, thanks. I'm going digital with this system. So we've been making a geological model of the materials beneath the Heretaunga Plains for 2 or 3 years now, and it's approaching completion. It was largely funded by government, core funding for GNS, urban geological mapping, but we had a very welcome contribution from HBRC. I've shown our team members up there, and what we're trying to do, and what I'm trying to do here today, is to build a skeleton of the materials beneath the Heretaunga Plains that the groundwater people can actually flesh out with how the water system works. And so what I want to do is just cover something about the contributing data, something about the effects of sea level change, Pleistocene sea level change, that's in the past, I'm not going into the future, and the consequences on the materials being deposited, something about uncertainty, and hopefully it'll all come together as a sort of a 3D representation of the shallow subsurface materials of the Heretaunga Plains. So next, please. So this is a geological map, and the light yellow in the geological map is the part we're interested in. The dark yellows are older gravels, and they lie somewhere underneath the light yellow materials. Next, please. So if we crank that over and look at it from the side, and then say to ourselves, well, what's underneath? So that's the next one. So we've got a network or a lattice work, pretty sparse, of seismic profiles. And those seismic profiles tell us very little about what's in the top 500 metres of beneath the Heretaunga Plains. And of course, that's the bit that we're interested in. But they do provide a framework on the structure of the materials beneath, the deeper materials beneath. And so we can carry those structures up into the younger sediments. Next, please. Throw on top of that a whole lot of water well borehole logs, and there they are at the same scale, which is about 1 to 10, I think it is, vertical to horizontal. And you can see that the boreholes actually don't go very far down beneath the surface at all. So next, please. I don't want to dwell on that one. We'll move on to sea level change through time. This, you probably won't be able to see it, but this is 500,000 years worth of sea level change. The top is where we are today, and if I trust myself with this gadget, this point in here, 20,000 years ago, sea level was about 125 metres lower than where it is today. And so there's been so much change in sea level, we have to understand the effects of that. So next, please. So what we have is a sequence of warm and cool, just a cyclic sequence of warm and cool environmental changes. Next, please. And here we are 20,000 years ago. The sea shoreline was somewhere out about where I've illustrated it here at minus 125 metres. But wherever the coastline is, this is the point to remember, wherever the coastline is, the water that's fallen on the land actually has to get to the seashore. It's going to the sea. It has to get there, so there's a pathway between the land and the shoreline. Next, please. And we have a whole lot of geomorphic features that occur along coastlines, and you can look at the coastline today. This diagram is actually the Canterbury region, but it sits well with what we have here on the Heretaunga Plains. And up behind the orange and yellows, these are alluvial terraces deposited by a river, which is subsequently downcut. You can see the downcutting in the surfaces to the coastal plain, and you can see behind the shoreline there are a variety of features which include swamps, sand dunes, sandy areas, infilled estuaries, and even extant estuaries. But you change the sea level, and all those things migrate along with the shoreline. They take a little bit of time to regenerate, but that's what they do. So next slide, thanks. Okay, we can go through these fairly quickly. So we're talking about sea rising here from that low sea level of 20,000 years ago. It pushes a zone of swamps and reduced drainage in front of it, and then the sea overlies those deposits that were previously deposited on the land, so alluvial deposits. Next one, thanks, and the next one. And at the same time, as sea level stabilises, sediment flow is coming along the shorelines, and it can form these barrier bars around the outside of an estuary. And then slowly, next one, thanks. As when the sea level stops rising, then the materials coming into that estuary from the rivers rapidly infill the estuaries. Next one, thanks. And then when sea level drops again, you find that non-marine materials are deposited on top of marine materials. So the next one, thanks. I've got to cut through these fairly quickly because we haven't got much time. So this is another diagram for Christchurch, and it shows that in the plains area of Christchurch, around Christchurch City, there's an alternating sequence of alluvial gravels and marine deposits. And for Christchurch and for the Heretaunga Plains, the marine materials and the swamp materials form a great aquiclude, or a cap on water which is in the gravels below. And that's a wonderful, that's a tonga. Next, please. So I was going to talk a little bit about uncertainty. I won't go on too long, but the point I want to make is that there's uncertainty in the geological map at the surface, and this geological map is the most certain part of our model. I want you to remember that. There's everything that we build up in the modelling depends on borehole logs. We rely on the accuracy and reliability of all those drillers and people who drew the logs, and we also rely on information where it's present, and as you go deeper in the ground, that information becomes more sparse, and so our model becomes more uncertain. So those are the things that I really wanted to say, that we have this conceptual model that we've gone through, and we now use the data which is available to hang our geological model on that conceptual model. So next, please. I hope this is clear to you. this is our geological model for the Heretaunga Plains, and where you see green, I want you to think gravel, and where you see pink or blue, I want you to think about fine-grained materials that are less likely to conduct water. So next one, thanks. Oh, I should say before, if you can remember that, there it is. Forget about the golds, the gold colours. They're what we would describe as the basement. They're not going to hold, other than limestone, they're not going to hold a lot of water. Next one, please. And so here we are, we can slice our model across the basin. So this is basically from Napier to the Tukituki River. And next one, thanks. We can slice it along. So this is a series of volumes which occupy discrete three-dimensional edges, and we can slice it any way that we like. Next one, thanks. So we can slice it horizontally as well. So that particular view is sliced at about 9 metres elevation, I think, plus 9 metres elevation. So the materials behind Hastings, we're actually slicing into the ground surface, below the ground surface, whereas the materials seawards of Hastings, of course, it's much lower, and we see the surface involved. Next one, thanks. So what I'm going to do now here is take you through the deposits that we've modelled for materials subsequent to about 15,000 years ago. And so I want you to think back to the sea level curve and remember that sea level's rising from this period. At this period, when this image was, this slice is cut, sea level was probably 20, 30 metres below the current sea level. And so as we go up through the sequence, I hope that you'll see a pattern of what's emerging. Let's just give it a go. Well, oops, we missed the key thing there. No. There's a movie there, and I hope we can play it, because if we can't, I'm not going to illustrate it. And I'll go straight on to the conclusions. There should be a little bar at the bottom of the movie there. So if you go back two. This is what I always hate about these. So if you maximise that, go back onto the screen view. Or you can hit that button if you like. There we go. Look at that. That's the way. Yeah. So here we go. Sea level is intruding or transgressing across the current shoreline and up towards Hastings there. And by the time it gets to the maximum, which is about there, it's about 6,500 years ago. And then, as you can see, it rapidly disappears during the period from about 6,000 years ago to the current, pre-1931, it disappeared off the Heretaunga Plains. So this is about, let's say, about 12,000 years or 14,000 years covered in 20 seconds, okay? So if you play it again, maybe, you'll get, what I want you to show you is that the pink swamp materials just advance across the landscape. Yep, that's the one. Advance across the landscape in front of that blue stuff. You see the swamps in front of the marine materials. So we've identified those marine materials on the presence of shells. And the swamp material is loaded with wood. That's enough, thanks. So this is a three-dimensional. What I want you to look at is that there are some fans, some alluvial fans that are coming out of the Ngaruroro, out of the Tukituki and out of the Tutaikuri. And those fans are deposited from streams, rivers that are flowing to the coastline constantly through that period of time. And so there are gravels within what we think of as the aquitard. And those gravels are permeable, and I'm not going to say anything about the groundwater stuff because I'm not a groundwater geologist. That's to come. So I'll just say these conclusions, that the last glacial gravels have been modelled, as have the marine sands and silts that overlie them and the swamp materials overlie them, that the Ngaruroro, Tutaikuri and the Tukituki rivers have continued to flow through the Heretaunga Plains to the coastline through this whole period of time, and probably beforehand as well. Excuse me, please. It's likely that the basin, the Heretaunga Plains basin, is actually structurally controlled. In other words, there are some active faults that are going through the basin. And I'm not going to, I have guessed where they are, but I'm not going to go into that right now. But in places, these young river gravels, very young, that are being deposited today that are permeable, are sitting on the last glacial gravels with nothing in between. And so I don't know, I expect that our groundwater people might have something to say about that. The next slide, I think, I did have a question, something about aquifers and earthquakes, and while I'm not a groundwater person, I'm prepared to give it a shot because I've talked to one of the people who's been heavily involved in Christchurch. So every earthquake's different, and every subsurface sequence is different, and so there's no one answer to that question. So the next one, thanks. But what you normally get with an earthquake hitting an aquifer, particularly a confined aquifer, is that there's a pressure pulse, like a spike, a peak, and you can see in the left-hand diagram each one of those has got a pressure peak in it. But some of them, the response changes. So the blue one at the bottom, for example, previously had a high water pressure, and subsequent after the peak, it had a lower water pressure. The red one, it had a spike, but it just continued, the water pressure continued to rise after the earthquake. And so there's a whole variety of responses that individual boreholes show to the same earthquake. Next, please. So the aquitards, or the fine-grained materials sitting on top of an aquifer, may be stressed or even punctured. And the next one, thanks. And that process may actually involve release of water from the aquifer to the surface. And in fact, there's some strong suggestion that that's what happened in Christchurch, and hence so much liquefaction in the eastern suburbs. Next, thanks. Over time, there's a process of aquifer healing in restoring it to something like its previous state, but the time frames are likely to vary. And then the final one, thanks. So changes can be permanent, and in the Canterbury area, some of the inland boreholes have been permanently changed. So that answers the question. I don't know who it came from. I hope it helps everyone. Thanks very much. That's all I had to say.
Can I also just say that at a conference I was at on Monday, I was told that post the Kaikoura earthquake, there is now major treatment facilities being put in Lower Hutt, and they can't explain peaks in, I think it's fecal coliforms that have been found in Christchurch. So there's things going on that we don't understand, but we shouldn't think that we're immune from earthquake impacts on aquifers, because it appears to be an issue somehow. We don't understand it. So, right, it's now my pleasure to welcome Jeff Smith, the Principal Scientist of Hydrology for the Hawke's Bay Regional Council, and you are going to tell us what's going on underneath.
I appreciate it. Oh, thanks. Kia ora koutou. I'm lost without slides, to be honest. I hope that's 2 seconds, not 2 minutes.
Here we go.
Saved. Thanks very much. So, yeah, with all the pressure in the world, my job today is to talk about understanding the Heretaunga Aquifer. So I'll start off with a description of the aquifer system, building on from that excellent presentation that John just gave, and then talk about groundwater use in the plains, the monitoring data that Hawke's Bay Regional Council collects in terms of groundwater levels and quality. Then look at some modelling that we're doing to inform a regional plan change. It's also been referred to as the tank plan change already in this forum. And finally, I'll look at some future research that is potentially going to be done next summer. So, just to start off with, this is what's known as the Heretaunga Aquifer system, because it's a bunch of aquifers in there, and the colouring is kind of similar to what John showed. The pink area there is what we call the confined area, and the yellow is the unconfined part of the aquifer system. I'll just point out that although there's hard boundaries on that map, the confined area, it's all within there, it's degrees of confinement, so especially around the borders of that confined area, some areas will be less confined, there'll be some areas that are semi-confined which have a pathway, but there's also, just want to point out that I'm talking about groundwater, but it's really one system we're dealing with. Groundwater and surface water are connected, and when we do our research, when we do our investigations and monitoring, we consider it as one resource, and you can see these green dots here represent springs where the groundwater is discharging to surface water. I'm just going to move this thing. Hello? Cool. So also in here we have interaction with surface water. These areas here are where the rivers are gaining water from groundwater, and the red areas are where this is the Ngaruroa River here, and the red areas are where it's losing water to groundwater, so it's recharging the aquifer. And most of the recharge in the Heretaunga Aquifer system comes in this losing reach here, where water is lost from the Ngaruroa River and actually travels throughout the aquifer system before discharging out to sea. And if we take a cross-section of the aquifer system here, we have the hills up here, rain falls on the hills, and also falls on the unconfined area where recharge occurs, but as I said, most of the recharge is from the river. So we have water disappearing from the river into groundwater, and those silts and clays that were laid down during the marine transgressions that John described before, they create the confined area. So up here you can have a non-flowing well in the unconfined area where you're having to pump water out, and down here in the confined area, water's artesian because the pressure's created up here, which is at a higher elevation than down here, so your water discharges without pumping above the ground surface. There's also natural springs in that semi-confined area in here, really. And then finally there's discharge out to sea. So we're protected by these clay and silt layers, but as I said, they're not always continuous. And also another thing to note is that water in these parts of the aquifer can take days or months to appear, to travel through the aquifer system, but down here it can take decades, and Uwe's going to talk more about that in his presentation following. In terms of water use in the aquifer, this is a map showing all the consented authorisations for groundwater abstraction, and you can see some of the bigger ones in here. They are generally the public water supplies. Well, there's fewer of them, but they do require quite a substantial amount of water relative to these smaller ones. But it's the smaller ones, mainly from Roy's Hill eastwards towards the sea. There's so many of these small ones that there's actually a substantial amount abstracted from those as well. And in terms of how that's changed over time, this graph shows us. So in this graph we have million cubic metres over here. 1980 to 2014, the amount of abstraction from groundwater has increased over time. This is the public water supply actual use down here, which has remained relatively static. Industrial use here has increased a little bit over time, and abstractions for irrigation have increased quite a lot since the 1980s. There's also some very relatively small abstractions for permitted domestic takes, frost take and stock water here. This is quite interesting, this one here, which is below the zero marker there. That's because that is a take that used to come from the Naruroro River and was discharged into the aquifer via recharge pits, so it's what's called managed aquifer recharge. That operated from the late 1980s to 2008. Am I doing something wrong, or the batteries need changing in this? There we go. Oops. Technology, eh? Come on. There we go. So this is the recharge scheme that operated these soakage pits here, where water was taken from the Naruroro River through some races and discharged over these pits where it seeped into the groundwater. And you can see in the graph that I showed that that's quite a large volume of water that was being recharged to the aquifer to supplement what was already naturally occurring. One of the things about the irrigation takes, that was annual average, that was the annual groundwater volume abstracted. One of the things about the irrigation takes is, of course, that there's more water taken during summer, and so therefore those abstractions can increase the seasonal variability of the takes as well. And one of the questions we have at Council is, we need to monitor whether the groundwater levels are declining over time due to those abstractions. So we do state of environment monitoring of groundwater levels. There's a bunch of over 20 sites in this map, and we have data here from 1994 to 2014 that was used to evaluate trends. So the blue dots in this map, these blue dots here, are where there was no trends observed in the groundwater levels. The red triangles pointing downwards are where there has been declining groundwater levels during February. As I said, we sort of need to focus on summer because that's when most of the abstractions are occurring. So if we look at the February trends, there's about 10 centimetres on average per year declining from that well near Roy's Hill, and about 7 centimetres from this well, 10371. it has been suggested that that could be due to increased abstraction in the area. However, there's another explanation I think is equally or perhaps more plausible. If we just go to the next slide. If we look at that bore 10371, this is the data from 1968 to 2014. If we run a trend, you can see the seasonal variation and how it does increase through here. And if we look at the trend line through here, we can see that there has been periods of decline. But that seemed to stop. It was declining here when there wasn't a lot of abstraction going on anyway, and then it seemed to stop here. And that's when that managed aquifer recharge scheme was first trialled. So there's a substantial take for that from the river put into those soakage pits. The scheme was commissioned in 1988 with a substantial amount of water. It was 3 cumecs, I understand, was allowed to be taken and put into those recharge pits. And then in 1995, there was a consent change which reduced the amount of take to 600 litres a second. And then in 1997, the consent was changed again so that the minimum flow for the river was raised. So there was a lot less water available to be abstracted for that scheme. And coincidentally, perhaps, or not, the groundwater levels have started to decline again. And the scheme was finally abandoned in 2008. So that presents another explanation, especially the fact that those groundwater levels are declining only in that area and not throughout the plains. We also monitor state of environment groundwater quality at a number of bores throughout the region. This is for Heretaunga and Ruataniwha, but we'll focus on Heretaunga here. One of the variables that we monitor for is E. coli, which has been talked about before. These data are 2014 to 2015, so the New Zealand drinking water standards of New Zealand specify that you need to have zero, absolutely no E. coli in raw water for it to be considered secure. So our state of environment monitoring in Heretaunga shows that generally that is compliant with that, but there's one site here, not far from here, where E. coli has been detected on numerous occasions. I just need to point out, though, that that well is only 8 metres deep. The drinking water standard specifies that groundwater can't be considered secure unless it's greater than 10 metres, and then there's a whole lot of other hoops to jump through as well, as Brent talked about earlier today. So that's kind of an anomaly, that well, and we're considering that it's not really of value to the State of Environment Network, and it's being replaced with one at a more appropriate location nearby. We also measure nitrate in groundwater, as Murray Close talked about the nitrate nitrogen before. Generally, there's very low levels of nitrogen in the Heretaunga Plains groundwater. There are some sites where it's an issue, and these are generally the shallow bores, as Murray talked about earlier. Don't tend to find it in the deeper bores. There's a whole bunch of groundwater quality variables that we monitor for. I'm not going to go through them all. They're the main ones. We also have samples analysed for iron concentrations, manganese, and total hardness. So down in the deeper aquifers, you find higher concentrations of dissolved iron and manganese, and that's because of the residence time. The groundwater spends a lot of long time down at those depths, has a lot of time to interact with the rocks and becomes mineralised with those. And that's not ideal for drinking water either, as is total hardness. If groundwater's flowing through limestone, you can get quite a lot of hardness in the water, which isn't good for pipes and appliances, not to mention the taste. And Murray Close also talked about the pesticide surveys before that HPRC contributes to, and it's good news that there's been no pesticides detected in any of those surveys. Groundwater is a fairly simple word, but it's quite a complex topic to talk about, so I'm really rattling through this in the interest of time. I did want to talk about the modelling that we're doing to inform a plan change in the Heretaunga Plains. This is being used to inform the tank group who are making decisions on how the water may be managed tank catchments. So what we've built is not a model, it's a bunch of models that integrate to form this groundwater, surface water model. And we have a groundwater model up here that is a part of it. Also a groundwater nutrient transport model, a surface water model, and we haven't just built this on our own. We wouldn't have had a hope, so we've been really well supported by the likes of GNS Science, and also the New Zealand eScience infrastructure. We probably couldn't have calibrated the models at all without using a supercomputer cluster that's hosted by Auckland University, which is basically the equivalent of using thousands of computers to calibrate this model. I think we've used 65,000 core hours, which if we were trying to calibrate the model on one computer, we'd be coming back 7 years' time to get the results. So it would have been impossible to calibrate it without that support. Along with Williamson Water Advisory in Auckland, building the surface water model, Aquilink Research and NIWA, and also the University of New South Wales in Sydney's been involved with the transport modelling. So it's a really sophisticated model, and what I'm going to show today is just some results that barely scratch the surface of what we'll be using it for. But this is the domain of the groundwater model, the boundary around the groundwater system. So everything within that we are modelling in the groundwater model. So it's quite a high resolution model. The grid that we use for modelling it is 100 metres by 100 metres. So in terms of a regional groundwater model, that's pretty fine scale. And we also need to include surface water modelling in there for two reasons. One is that surface water enters the groundwater system at the boundary, and we need to know what that is. And also the interaction of groundwater with surface water within the Heretaunga Plains needs to be modelled. So we have a surface water model with over 100 sub-catchments that go right back up to the top of the Ngaruroto River, and each of those sub-catchments has its own separate model in there that interact with the groundwater ultimately. One of the first applications we used the model for was for stream depletion modelling. Now, stream depletion is when groundwater abstraction causes water either to be induced to flow from a stream into the groundwater system, or when groundwater is intercepted that would have otherwise made it to a stream. So what it is basically abstracting groundwater and losing stream flow one way or another. Here's one scenario when that happens is in spring flows, when water is intercepted before it can discharge into springs, or here like in a lowland stream where water might be caused to flow through the stream bed and into the groundwater. So to model that, we've got the confined and the unconfined areas in the aquifer, and what we did is calibrated the model. One of the parameters we used for calibrating too were the observed spring flows and river flows. So we were able to match currently what's in the springs and rivers, and then that allows us to calculate stream depletion. What would happen if we changed pumping, for instance, within the Heretaunga Plains? What would happen to those streams and rivers? So we ran the model over October 2012 to February 2013 to run the simulation over what was a very dry summer. And we ran the model without any pumping in the model and calculated the surface water interaction. Then we added one pumping well, which should be one of these dots. So put a pumping well there, run the model again for a certain abstraction and calculate the difference in the stream and river discharges. And the difference between that and the model that was run previously without any pumping is the stream depletion impact. Then we can calculate the percentage of stream depletion. So we ran that for different time periods and at all of these locations across the Heretaunga Plains to calculate the stream depletion effects of pumping at any location in the plains. And what we found was that there were these directly connected groundwater takes in these red areas. So after 7 days of pumping, 90% of that water is being from streams or rivers. And then following the Tuki Plan Change 6 framework, we decided to model 150 days of pumping, and anything that had more than a 60% stream depletion effect is within this blue area, pretty much all of the plains area. And under the Tuki plan change, all those takes would be restricted in terms of when the flows in rivers and streams drop below certain levels. So that would have a widespread effect across the plains. There's also these orange areas here, where after 30 days of pumping, more than 60% stream depletion effect is observed. So that presents a bit of a dilemma in terms of water management, because on the one hand, that would have enormous economic consequences across the plains if all of those takes were restricted during periods of low flows. And furthermore, putting them on bans wouldn't really be that beneficial to the streams anyway, because it takes so long for the streams to recover after the groundwater pumping stops. So, as I said, conventional management options, including the pumping bans, would have widespread economic consequences and generally effective at protecting the stream flows. So then we can use the model to explore other options for managing those groundwater takes, or ensuring that stream and river flows aren't compromised, and that includes augmentation of stream flows from groundwater, which is already happening in the Raupari stream. The Twyford Irrigators Group are successfully taking groundwater during periods of low flow and augmenting the flows in the Raupari stream, so the flows aren't compromised by groundwater takes. And another option is to explore managed aquifer recharge in A, different locations, and B, have more of them across the Heretaunga Plains. We can look at what mitigating effects they would have on those stream depletion effects. So we're working with the TEMP group now on that sort of modelling. Okay, thanks. Just looking into the future, there's also, John's leapfrog model represents the best conceptual understanding we have of the Heretaunga Plains aquifers, and it's a great interpretation tool, and it's a great visualisation tool for taking the data that we have from bore logs and other geological information and turning that into a conceptual model. But as John said, there is uncertainty in there, and especially in those areas where the level of confinement is kind of unknown, and the aquifer might be semi-confined, we really need to know more about that. So next summer, we're hoping to undertake some research with GNS Science, doing an airborne survey of the Heretaunga aquifer system, or parts of it. And what it means is taking a electromagnetic instrumentation here, flying transects with a helicopter across the Heretaunga Plains. Obviously this isn't the plains area, but that's the equipment that's used. It provides geological mapping, subsurface mapping at an incredibly fine detail in 3 dimensions, and it can see through hundreds of metres below the ground. So I show this as a sort of profile you get from one transect flight with that. These data are from, it's about a 400 metre depth that they're looking down into here, and it shows you all the fine detailed geological structures within there. And I think Liz Lambert, when I showed her this yesterday at HBRC, said it's like an aerial photograph that looks under the ground. And you can take those data from the airborne survey, match them up, or apply the bore log data as well, and what we know about the hydrogeology, and produce these really fine detailed 3-dimensional maps of what's going on under the surface. So that can tell us, for example, if confining layers are continuous, how deep they are, and incredibly useful, valuable for not only our modelling and understanding of the aquifer, but it will also be really valuable for other organisations, for instance, people who are looking for secure groundwater supplies, for instance, or wanting to know where they could abstract some water for irrigation without having to spend money on expensive drilling. So as I said, it is quite expensive. To do the whole plains is cost prohibitive. We're not an incredibly wealthy council, but we think the best bang for buck would be to focus on these areas here, where there's quite a high connection to surface water, and around that confined, unconfined boundary area where we really need to know more at a higher spatial resolution. So as I said, we're hoping to collaborate with GNS Science on this one. It depends on success with a funding bid to MB. And if that is successful, if GNS is successful at that, then we're proposing to survey in next summer, and focus on those key areas of the Heretaunga Plains. There is an opportunity for local collaboration as well. And when I mentioned this to Liz Lambert, she asked, am I going to pass a hat round today? Which I said, no, I'll probably go through a more formal process than that, but I know there are people in this room who will be interested in this research, and we're really excited about co-funding and collaborating with others on this work. And that brings me to the end of my talk, but I really need to acknowledge that, I'll summarise first. There's evidence of those groundwater level declines in one area of the Heretaunga Plains, and as I talked about earlier, that's possibly caused by cessation of that managed aquifer recharge scheme. Water quality in general is good, even though Andy said it's a real general term that we try to avoid. Generally, it's good. There is some shallow groundwater that has higher nitrate concentrations and E. coli, and the deeper aquifers have elevated iron and manganese, but there is good quality groundwater in the aquifer system. We're using that sophisticated model to inform water management decisions for a plan change at the moment. And future research opportunities include that airborne geological survey, which would tremendously improve our knowledge of the groundwater resource. As I mentioned before, there are some people I need to acknowledge: GNS Science, Aquilink Research, and the supercomputer made available by NESI. But more importantly, the team, the HBRC hydrogeology team, Simon Harper, Dougal Gordon and Pavel Rakovsky, they did all the work that I've shown today, so I can't take credit for that.
Okay, it's now my pleasure to welcome Uwe Morgenstern, who is the team leader from Isotope Hydrology and Water Dating Lab for GNS Science. And what this presentation is the next part of the understanding, really, which is about the age of the water under the aquifer, or in the aquifer. Yeah, hold it.
Kia ora, and thank you to the organizers for inviting me to this very interesting symposium. So we heard from John about the container of the groundwater, and Jeff has talked a little bit about the groundwater flow model, and I will talk about groundwater dating, which can be used to validate the flow model. So we can basically measure the age of the water, and if a model comes up with the same answer, then the model is basically doing the right thing. And what's also important here is that, so I will talk a lot about tracer data. So basically I'm letting the water tell the story. So we are looking into the chemical and the isotopic signature of the water, which can tell us where the water has gone along, where it has been recharged, and how long it has been in the ground. So first I will give a little bit context about how can we measure, so basically how old is the water and where does it come from? So how can we answer these questions? And then I will talk about recharge sources and groundwater age in the Heretaunga Plains, which we have so far, and give a little bit an view to what we are going to do in the next future. So this work so the tracer data has been produced by a team. So on the left side, you see the team of the water dating lab at GNS, and on the right side, our groundwater modelers. How can we measure the age of the water? So we have a groundwater system here, and we can basically measure. So with the water, with the rainwater, there are tracers in the water which we can measure, and we can, for example, if a tracer has like a peak here, and we can measure how the tracer moves through the groundwater system, so it rains into the system, and this is the discharge of the groundwater, so it's a stream or it could be a well, and we can measure the concentration of the tracer over time in that discharge. So we see, and this is a real example here, this is Hamurana Spring, or it's called now Hangarua Spring, Lake Rotorua. So this is the tritium input signal into the Rotorua catchment, and this is what we measure in the outflow. So we see that the tritium is much lower, so tritium is radioactive, so it decays, so the water is very old. So that means, so in this case, the Hamurana stream discharging into Lake Rotorua, that water is 125 years old. So between when it rains into the catchment, picks up the nutrients, and until it goes into the lake, there's a big time lag. Murray Close also mentioned this in his talk. So what is also important is we need to apply a model, because obviously groundwater is a mixture of different flow paths. So there will be long flow paths and short flow paths. So we have young and old water mixed together. So we need to apply a certain model, and this is showing the exponential piston flow model, which was state of the art until now. So, and I'm just giving you a little bit information about the tracers which we can use to measure the age of groundwater. So what we see here is tritium. This is the natural cosmogenic tritium. So this is over time, 1950 to 2010. We see that this is the natural tritium. So tritium is produced in the upper atmosphere by cosmic ray interaction with the atmosphere. So we see a very little amount of tritium is being produced and in the rain. Then some of you probably remember in the early 50s there was the nuclear weapons testing period, which during the hydrogen bombs, so tritium is hydrogen, so there was also a lot of tritium produced during these tests. And what we see from these tests is that spike. So that spike we can basically track through the groundwater system, and this is a very efficient tracer how we can measure the age of the water. But it is also causing some complication, because this is radioactive. So that water was 50 years ago. So it basically has already gone through 5 half-lives of tritium. So it's basically now completely decayed. But 30 years ago, it was about the same concentration as young water. So it was difficult to distinguish between young and old water. So, and for that, we have complementary tracers. Here are the CFCs, so chlorofluorocarbons. Some people probably also remember they have been used heavily in refrigeration and spray cans and so on. And that caused the atmosphere, so the ozone layer, to deplete, and that's why they have been banned. So that's why we can't use them as tracers anymore. So they are basically flattened out here. But we have one very efficient tracer, which is sulfur hexafluoride. It's coming from electrical switchgear in small amounts released to the atmosphere, dissolving into the rainwater. So we have an ever-increasing concentration in rainwater, and we can measure the concentration in the groundwater, so we can relate it to the time when it was basically recharged. So that's the age tracers. Then we have also tracers which can tell us about where the water has been recharged. And here are the stable isotopes. We have, so this is the hydrologic cycle. Water in the ocean has by definition 0 ratio, and when it evaporates and recondenses. So these are all kinetic processes which change the stable isotope composition, and depending on the temperature and the altitude and how much it has moved inland, we have a different stable isotope composition. And that is... Oh. Yeah, so thanks. So what we see here is we have very negative stable isotope composition in the Southern Alps, for example, and different, so more positive in the Canterbury Plains. So the rivers coming from higher altitude, they have a different stable isotope signature. The same occurs here in the Heretaunga Plains, not as much, but we can still pick it up. When we have different tracers, so gases are being dissolved into the groundwater. We have here the situation, this is the groundwater table. Rainwater gets on top, has air bubbles in it, and these air bubbles over time dissolve. The next rain parcel sits on top. So we basically dissolve excess air into the water, and that enables us to distinguish if the water has actually been recharged from local rain, which is going through a groundwater level, or it has been recharged from a losing river. So, and this is a bit faint here, but it clearly shows, so water with high excess air is being recharged from local rain. When we have hydrochemistry, we have we are measuring a whole raft of hydrochemical parameters. We can do cluster analysis on these, and that enables us to look how similar waters are between each other. And that is just the study which we just completed in the neighbor region here in Horizons, where we can basically very nicely distinguish which waters are similar to river water and which have gone through a completely different history. And this is some of a significant figure now for the Heretaunga Plains, which has kept me very busy over the last weeks. What we see here is we have these symbols, and the green color represents rain recharge, local rain recharge, and the blue color represents river recharge. So what is very clear here is that all of these groundwaters down here, they are recharged from rain. And up here, so in this area, we have river recharge, and up here, very clear river recharge signal. So this is a little bit different to what the understanding was so far, and so this is still ongoing work. I'm still working through additional tracer data to basically fill in more and more of these gray areas which haven't got a color yet. I will just show a little bit, talk a little bit about the groundwater models, and one of the problems which occurred here in the Hastings District Council water supply. So we need to apply one groundwater flow model. To give you a little bit in context, so this would be a highly mixed model, and we call it an exponential model, where short flow paths and also long flow paths all combined in the well. This would be a piston flow situation where all the water has one age. And normally we use the combination of the two, which is called the exponential piston flow model. And that model has been able to model the data which we have produced over the last 30, 40 years very well in most of New Zealand. So the situation is, however, a little bit more complicated in the Heretaunga Plains, and this is a geologic cross-section which John produced from his wonderful model. So what we see here is, here are shown the Brookvale wells, but they are actually tap into multi-layers of aquifers. So and they basically, so that means that old water from down here can basically, or young water from a shallow flow path can be hidden in mostly old water which is coming from a deeper aquifer. So basically we have to revise our understanding about groundwater models here completely. So this is just showing the data which this is Tucker Lane in Clive. So we have the tritium data here, and we can very well match that tritium data with that blue curve, which represents a mean residence time of 42 years, with that mixing of 33% of mixed flow. So that and that, so what we have now is we have also another tracer now. I explained it before, SF6, and that gives us additional information. What we now see here is that this model, the blue curve, does not match the SF6 tracer data. So, and it also doesn't match the tritium from the last round, which was in 2016. So we see that this basically was, we could match this basically this tritium decay here with the wrong model, and that the more recent data show that there's actually also much younger water. So the tritium is higher than it should be here. So there's younger water in that well, and what this red curve would represent an age of 15 years. But the 15 years also doesn't match the SF6 data. So there is some more complicated mixture in that well. And that is explainable by the multi-screens of these wells, which can have basically old water and some contribution of extremely young water, which is in high, in very good connection to the surface. So and, this new model is this green curve here, which basically can match very well all the tritium data and the SF6 data. And what the difference is you can see here, the blue model curve, which we had applied before, would have this age distribution. So the youngest water would be about 28 years. But with a new model, which is basically calibrated now to the two tracers and also to that. So what's different now is that the bomb tritium, so the bomb tests were 60 years ago, and that bomb tritium is now completely decayed, so it doesn't interfere anymore with our interpretation. So basically now we are not having that interference anymore. So what we now can clearly see is that we are not having this age distribution, the blue curve, but it's the green curve. So we have a double peak. So that would be the shallow aquifer. This is the deeper aquifer, and that would be the cumulative curve. So that cumulative curve is, or that age distribution is still considered to be secure water. So we have heard several times today that the youngest water, or the younger the water, the more prone it is to be carrying live contaminants. So in what the Tucker Lane, so this well is still safe. So the youngest water in here is still 5 years old. But in the case of the Brookvale wells, that young component was actually only as young as a month or below a month. So here's the distribution of the drinking water wells, where we where I'm trying to highlight this, so it's a little bit complicated. In the squares, we see the mean residence time. The more red, the more young it is, and the more. And here, the circles are the youngest component. So what I just want to highlight here is this water, for example, has a very young mean residence time, but also obviously a very short piston flow component. So the youngest water is extremely young here. But in the Brookvale case, we have this reasonably old water, but still a very young component in here. And in general, what we see is, so in general, the older the water, the more safe it is for drinking. So what we see here is closer to the coast, we have the more older waters. And in these river fans, which John pointed out in his talk, we have extremely high conductivity, and the water in these wells can be extremely young. And this is the ongoing study we are doing. We have here data combined, which we are now or in the process of analyzing for all these tracers, and to basically get a better understanding of the whole Heretaunga Plains. So that data includes the Napier City Council wells, the Hastings District Council wells, which both have extremely valuable data because they have long-term data. And we also have some studies, the National Groundwater Monitoring System, the Hawke's Bay Regional Council has also done a survey, and other small surveys. So all that data is now being put together, and we are producing this. So we are basically investigating now how the groundwater system in the Heretaunga Plains works. I think I had another. Yeah, so this is quite significant. To highlight that we had to completely rethink our theories here. So this is data from across New Zealand, which I have just worked with, the light blue data. So this is tritium, which is the indicator for young water. So the higher the tritium, the younger the water, and plotted versus depth. So what we see is the yellow data is from the neighbor here, Horizons region. The light blue data is from the National Groundwater Monitoring Program, so which is all across New Zealand. And the dark blue data is from Southland. So what we see is that very little tritium mixes down into the aquifer. So the further down you go, the older the water. And if we now look into the Heretaunga Plains data, the gravels here are extremely conductive. So the tritium has mixed down at least twice the distance as we normally see in our aquifer systems across New Zealand. So this is a very strong indication, so basically not depending on any interpretation or model. So we just looking into the raw data, we see here that the tritium has moved down to 130 meter. So that means these aquifers are extremely conductive. So just to sum up here, we have looked into the recharge source. In the north, we have a clear river recharge. In the south, local rain. The Heretaunga Plains are extremely highly conductive gravels, and what we also see is very preferential flow paths, which can contribute extremely young water into what appears to be, in general, reasonably old water. So thank you.
Thank you. There's a lot in that, but essentially if we talk about trends, something looks like it's happening. We don't know quite what. But the new water concept and is being fed into your model, and we're soon going to get some answers. But just before I invite Nick to come to the stage, we really found this phenomenon when we tested in February of last year, and something was very different from what it had been before, so we can't explain it. And one of the reasons why the Hastings District Council is treating those bores that are in the red with UV really is to make sure that the system can be safe from the risk of young water until we understand it more. Anyway, I'm now going to bring Dr. Nick Jones forward as part of this panel, and then we'll have a wrap-up series of questions together.
Thanks, Lawrence. I asked Lawrence to put me in because I didn't want to be an orphan in the last session. I knew half people would probably leave. So thank you very much for putting up with me, adding a fourth presentation to this session. And thanks very much, everyone, for coming. I know a lot of you are taking time out of your day, and you're not doing this for a job. You're doing it because you think it's important. And I think we really appreciate that. Who would have thought we could thank the French nuclear weapon makers for giving us a tool to measure water age, eh? So I'm going to talk about water and health, and I want to start off with a discussion around a concept called Waiora, and I'm just going to try and bring us back to where we started at the beginning of the day and try and tie a few threads together. So this concept, or the way I'm talking about it, comes from a framework developed by Professor Mason Jury called Te Pai Mahutonga, and it's a way of thinking about how we promote health. And in his 1999 paper, Professor Jury talked about this concept of Waiora. He talked about 6 cornerstones, and as many of you know, Te Pai Mahutonga is also known as the Southern Cross, so it's an important navigational tool for us in the Southern Hemisphere. And in terms of health promotion, it's also an important navigational tool. For me, as a public health doctor specialising in environmental medicine, the Waiora part is particularly important because that's about the physical environment. The illustration that you can see actually comes from a report that I worked on quite a long time ago back in Auckland, Tamaki Makaurau in 2004. And the aim of that publication was actually to try and present a view of public health from a Māori perspective. So not only was it about the health of Māori people, it was about the health of the region, but as seen through a Māori framework, which is probably a little bit ahead of its time, but I think we're starting to see today the wisdom of that approach, and in fact how these different worldviews are actually starting to come together. Drinking water, of course, is fundamental for human health, and the improvements of drinking water and the safety of drinking water in the early part of last century really accounted for major improvements in reductions in infant mortality. In New Zealand, the sanitation movement began actually in the middle of the 19th century. This photo just shows Auckland, Queen Street, with a great big canal running down it in the 1860s, full of sewage. And obviously they were having difficulties back then. Moving on, we also had predominantly the use of backyard wells for water supply. Certainly that was the case in places like Hastings where there were wells were available. By the 1890s, the sanitation movement was really just starting to develop. Let's see if I can get that to go. Here we go. This shows a map in 1892 of a typhoid outbreak in Wellington. You'll see you may recognise some of the street names there, Toria Street, Courtney Place, and there was a big cluster of typhoid cases at that time. So someone did some clever mapping work and figured out that they were close to stormwater and sewer pipes, which were blocking off. So this, as was alluded to earlier today by Brent, this need to separate wastewater from drinking water we've been understood this for quite a long time. But even in Hawke's Bay, there's some records to suggest, this was from a text from 1940s, that Hawke's Bay was recognised to be prone to waterborne disease where the soils were prone to pollution and water could become contaminated. So we have been aware of these issues for a while, but perhaps we've become a little bit perhaps blasé about it, or maybe lost our memories about it. What are the water issues today then? So obviously we need to think about the benefits of water for health. We've already talked about that quite a bit. But also, what are the risks? So the risks are around microbes, chemicals, we've already talked about. Also, I want to very briefly talk about the risks for people using the water for recreation. And how do we go about preventing and detecting those contamination events? I won't really dwell on the benefits. I think we all understand those. It's necessary for our bodily functions, of course, but it also provides for all those positive aspects of human life. And then it provides also ecosystem services that not only is it important for the animals that are within the ecology, but they provide for actually human benefits as well. And of course, it's a basic requirement for our production of food and for our economy. The first risk I want to talk about, though, is actually not having enough water, and that actually is a very real problem for some people in our region. So we have rainfall-dependent communities, as well as communities whose groundwater is from more superficial layers within the aquifer. The rainfall-dependent communities tend to be up the coast or down in Central Hawke's Bay, and with increasing climate change, we know that those communities are going to become more vulnerable to long periods of lack of rainfall. In the groundwater, we know that also that there have been people who have lost their water supply through pumping, and who in summertime, bores that used to flow have stopped flowing. I don't need to talk about the risks from microbes. Brent has covered that off very well. Needless to say that last year in August, we suffered the largest Campylobacter outbreak recorded in the world. And this is what the incidence of cases looked like over those few days. A massive number of cases were reported to us. The ones that we heard about were ones that were seen by doctors, of course, which was just a small proportion of the total number, and we estimated that total number using household surveys. Subsequently, this map just shows that actually it wasn't just people in Havelock North. There were people who had consumed water from Havelock North who resided in Havelock and further in Hastings and further away. Subsequently, there have been people suffering longer-term effects. Depending on how you measure it, between 2 and 23% of people developed some kind of arthritis as a result, most of which would have been resolved, but some would have had longer-term issues. Kidney and bowel problems occurred at the time, and 3 people developed a syndrome, a neurological syndrome that causes partial paralysis. One was severe enough to need ventilation. And then there's been another more sort of general effect, which is harder to quantify, which is really the effect on the elderly who got the disease and who became less mobile, became more frail as a result, and in some cases have never fully recovered. I don't want us to forget also that there are people who supply their own water from the ground or from the surface, and in some ways there's even more risk to those people because they don't have often the monitoring and the equipment to treat the water. There was a case a few years ago of a case on a farm where a child did develop STEC or VTEC that Brent described earlier, and we subsequently found that someone had unplugged the UV unit on the water treatment plant to charge their phone, and unfortunately that had resulted in a child ended up in Starship Hospital with kidney failure. So these can be very serious consequences. In general, in fact, up until last year, I would have told you that our biggest risks were in our smallest supplies, and this is primarily because they'd be supplies from superficial water layers or from the surface, and generally without protection against Giardia and Cryptosporidium. Of course, the way we measure what is a compliant water supply is likely to be reconsidered as a result of the outbreak. Just a little bit about some of the conditions that are commonly referred to as being associated with water, and these are Cryptosporidium and Giardia. One of the things we notice when you look at the data over a period of years is that there seem to be with crypto actually two peaks. So one occurs in spring, and then there's another peak in summer that also occurs with Giardia. And our working hypothesis is that this is something to do with recreational use of water, either in swimming pools or in rivers. There have been, from time to time, peaks in the incidence of these conditions in Hawke's Bay. We had a big peak a few years ago in crypto, which we attributed to recreational water use, primarily in swimming pools. Murray has talked a lot about the risks from chemicals, so I don't really wish to go into that in any detail. I did think I'd spend a little bit of time talking about methemoglobinemia, because that's, I think, probably one of the most relevant things to consider in relation to the nitrates issue. So the main risks with nitrate are actually attributable to the conversion of nitrate to something called nitrite. And nitrites are able to convert normal hemoglobin, which is used to carry oxygen in the blood, to something called methemoglobin, which is unable to carry oxygen. And people get symptoms when you get above about 10% of your hemoglobin being converted to methemoglobin. Normally, levels are around about less than 2% for adults and less than 3% for infants. Now, infants are actually at the highest risk, and that's probably because of their size. They don't have the enzymes to convert the methemoglobin back into normal hemoglobin, and because there's conversion by bacteria in their stomach, and there's lower levels of gastric acid, so the process actually allows more conversion of the nitrate to nitrite. The presence of bacteria actually in the water is probably very significant. So the early studies on the risks associated with nitrates didn't take that into account, and more recent studies have suggested actually it's the combination of the nitrates and bacteria in the water, or the presence of an infection in the child, that really increases the risk. Other risks around nitrates really are more theoretical, and they probably arise again more from the nitrite, but they are actually to do with the combination of the nitrite with something called nitrosatable substances. And the two combine to form something called an N-nitroso compound. I don't want to go into details about this, but the point about N-nitroso compounds is that they can cause cancer, and they can cause things like premature labour and reproductive health issues. Now, the nitrates in themselves don't have any of these risks, but obviously situations in which we might get nitrates causing increases in nitrites in combination with nitrosatable compounds, and some of those are things like medications like antibiotics and antihistamines. Potentially there are risks. All of this is very theoretical at the moment, and I think still being researched, but it's an area of active research, and obviously it's relevant to the issue of nitrates in the water. So where do the water contaminants come from? I think we've already had a lot from Brent about where the microbes come from, and also from other speakers around where the chemicals come from. I won't go into that. Before hearing my very erudite colleagues here explaining the Heretaunga Aquifer, I came up with a very simple diagram, which I'm going to have a go at it anyway. Because I think it sort of ties why is water age even important from a human health perspective? Well, this is sort of how I see it anyway. So some of the agricultural inputs and the human health fecal material coming from septic tanks can get into the waterways and get into the Ngāruaroto. And from there it can be recharged, the water can be recharged into the aquifer. And I've got a very simple aquitard here with just one red layer, which obviously is completely wrong. But some of the water goes in above the aquitard and some of it goes in below. And so the water that's going in above is going to be more subject to contamination from activities on the land. So, for example, if we are discharging our stormwater, which has contaminants from animal feces that are on the footpaths and washed into the drains and washed down into the aquifer, there's potentially a risk there for people who are drawing water out above the aquitard. Of course, we're taking a lot of water, and we've heard from Jeff and Liz, taking increasing amounts of water from the aquifer for urban use, irrigation and industry. And I suppose I have been rather simplistically thinking that we're also taking it out through superficial bores and also through these springs. But what I've been thinking about is, as we adjust the levels of the aquifer, are we actually changing the dynamics of the flow? And I'll be interested in what my colleagues here say. Because the reason that could be important is because of this. Pathogens, when they get into the aquifer, only last a certain period of time. And we think viruses, it might be up to a year. I think most pathogens, we would say, would be gone after 100 days. But if there is something that is occurring that is somehow increasing the speed with which that water has been transported, then it might become a relevant issue, particularly for people who are drawing water out of the aquifer, even in the deeper layers. Obviously, over in the case of the Havelock North outbreak, we now know that that was a much more complex situation, and in fact there seem to be two aquifers actually over the top of each other, the Heretaunga Aquifer and the Tamata Aquifer. Brett has already talked about the multi-barrier approach, and I'm not going to go into that any further, other than to say one of the things that I think is worth clarifying is the difference between E. coli, fecal coliforms, and total coliforms, because that people find very confusing. So total coliforms really are organisms that live in the environment, and they are an indication, they can be actually from vegetation and soil. 2 minutes. But where you get into fecal coliforms and E. coli, these are actually indications that there is fecal material actually in the water. I was going to talk a bit more about source water protection, and I think this will come up a lot more tomorrow, where we're going into, well, how are we going to respond to this as a community, and what are we going to do to prevent the water from getting contaminated in the first place. This just shows some predictions about what might happen to nitrates in the Heretaunga Aquifer that was done for the water storage scheme. And the current plan, one of the issues with the current plan from the regional perspective is that the current plan is a very simplistic approach to what's confined and what's unconfined. So, for example, we had those orange areas are defined as unconfined aquifer, but in fact we now know that the Brookvale bores were in an area that is defined in terms of our plan as being a confined aquifer, and so probably we're not getting protected in the way that they would have been if it was unconfined. I would just mention in terms of the recreational water quality, we're not focusing on today, but the areas that are actually affected tend to be areas that are in freshwater rather than the marine environment. And I can't do a talk without mentioning climate change and the implications of that for public health. It's increasingly recognised across the world now that this is the public health issue. Finally, there's been some discussion around sustainability earlier today. And there's an emerging idea that we actually need to start thinking about whether we move beyond the triple bottom line. So the triple bottom line is where we give equal weight to the economic, the social, and the environmental concerns. And then actually we need to change the priority and make the environmental the top concern, and the economy exists within that concern. Thank you very much.
Rightio, everybody. We have some time for some questions before we wrap up for the day, and there will be plenty of opportunity tomorrow as well. And will all you gentlemen be here tomorrow, or any of you? None of you. Okay, so we'll keep going while we can deal with this question, sir. First.
Thank you. You hear me better now? Yes, I think. I'd like to ask the probably UV there, Morgenstern. There's talk about deep aquifers and shallow aquifers and different water levels without saying what they actually are. And the primary concern here today would have initiated from, of course, the Campylobacter epidemic that we experienced. And it seems to me quite clear, sitting here and reading the inquiry report on the water contamination, that the problem with the Brookvale Aquifer is that it sources water at two levels. One shallowly at about 20 metres, as we've been told today, and at a much deeper level. Well, it seems quite apparent that the shallow water at 20 metres is wide open to contamination from the Mangatiri stream. That comes from dye testing and also regional council observation, according to their statement at the water report inquiry. To get around that problem, it seems that if you stick with the Brookvale Road Aquifer, you need to exclude the shallow water. You need to go down to the deeper, better filtered water. Failing that, would it be possible to go to an alternative water source away from that area, perhaps down to 80 or 100 metres, where the water is much better filtered naturally and is a much more potable level? Perhaps Uwe would like to comment on that. Thank you.
Yeah, so the shallow screen is actually in 12-meter depth, not 20. So 20 meters actually the deep screen. So and that 10-meter or 12-meter deep screen has a very high conductivity to the surface. So I also believe that if you exclude that top screen, the well might actually be secure if it only taps into the deeper aquifer. I'm not an engineer in that.
I can answer the rest.
Yeah, so probably. Yeah.
The other thing you should know is we have drilled down to 150 metres out of Brookvale to find water, and we didn't find any water that was potable or suitable for drinking. So the only other option, effectively, is to go to another part of the Heretaunga Aquifer and to upgrade the piping network to supply the water, which is exactly what we're doing now with the work that's underway in Napier Road, under Hastings, all that type of thing. So we have searched to try and find deeper water out here, and we haven't found any that's suitable. Other questions? Yes, sir.
What's the results of the water that you found at the 150 metres?
Yeah, apparently I haven't got the exact details, but it's high in heavy metals.
So iron, manganese type of...
Yeah, I haven't got the exact... Yes, they're nodding, yes.
So it's quite easy to treat that?
Apparently not, no.
I'm an engineer, yes it is.
Yeah, well my engineers are telling me no, so I'm not about to get into a debate about it here, but we did look at it as an option. Okay? Down the back.
Sorry, I just had one more question.
Oh yes, sorry, yes.
If we look at the aquifer is at the base of it's 20 metres?
I think so, yes.
Yeah, and the top is how far below ground?
Tony, 5. 5?
Meters. So if we're drawing from the aquifer, and it's a bit like how you have a static water head, I think it's quite shallow. I think it's maybe -3 metres.
It could be. Yes, that's right.
Yeah, so we're drawing from a 12-metre screen, or maybe higher, but if we're drawing from the screen, surely that would cause a significant reduction in the static or the water head once you're under pumping, so you'd end up with quite a significant suction from the surface water, or from the 5-metre area. So we could see that we would actually end up with drawing water from the surface. Probably part of the reason why we've got this issue.
Yes.
So it would stand to, sorry.
How and Tony, yeah, I'll let you answer it. I'm not the expert.
No,
Yeah.
that's okay. I'll let you.
Yeah, thank you. I'm Tony Cousins. I lead the investigations for Hastings District. Some of the information around the hydrogeology in the location of the bores and the Mangateretere stream was based on our work. So essentially what's happening there is the groundwater level, the confining layer is about 5 metres thick. So the water level, static water level is within that typically. When those bores are pumping, it draws down about 5 metres. So very high permeabilities through that area. So I mean, that's the advantage that the Brookvale bore field provides. So very high permeabilities. But what was understood until very recently in some of the dye tracer test work that was referred to was that there was no ability to draw surface water in because the confining layer was considered to be fully intact. So even though it was drawing down below the confining layer, that very dense layer that protects the groundwater and was always understood to protect that water supply, there was no ability to draw surface water down through that unless there was a defect. Now what we found and didn't understand till very recently was the defect was in the base of the Mangateretere stream pond. It was never considered to have lost water until very recently. It always was understood to deplete spring flow flowing into the stream, but not to deplete the stream itself. So, I mean, it's based on very, very recent understanding. Prior to that, it was considered that it couldn't draw surface water, even though it depressured the aquifer, it couldn't draw surface water in. So. Maybe I'll see.
Part of the problem with the testing is that it's grab sampling. You're only getting a short indication of whether it's age of the water or doing dye tracer testing. If you're doing it under flood conditions or under various conditions, because we know we only have a problem once in a while, can we trust the dye tracer testing, considering it's probably not being done under worst case scenario?
So I think one of the key things, there were 2 dye tracer tests. The first one wasn't, I guess it didn't fully reflect the conditions that we saw during the contaminating event last August. The second test did. We managed to replicate very closely the conditions within the pond. That was the water levels under flooding, the flooding condition we knew was there, and under exactly the pumping condition that we knew existed during the August event as well. So I think we can be reasonably confident that we very closely replicated the exact condition. This was in late January of this year, just prior to the inquiry hearing, and it replicated the condition that we saw last August. So I think we can have a very high level of confidence that that was pretty certain that that's what did happen in last August event, and I think that's what the inquiry accepted as being the conclusion as well.
Okay, down the back. David, welcome.
Jeff, just my questions framed around the 1998 Stu Clark report, which the contamination crisis we had last year mirrored. In it, he refers to the aquifer as a Tukituk aquifer. Could just a very simple question to you, Jeff. Are the bores at Brookvale Road sitting over the old Tukituk riverbed? And if they are, is that old Tukituk riverbed referred to as the Tukituk aquifer that runs underneath the Brookvale bores that supplied the water to Havelock North?
So is the question whether the bores are installed into the Tuki aquifer and withdrawing water that would have been Tuki water? Is that the other part of the question? Yeah. Yeah. Hmm. So yeah, it's true. There's the material in there is from the old channel of the Tukituki River. I'd ask John to talk about that too if you have any knowledge on that, but that's my understanding. In terms of it being Tukituki River water itself, that's not necessarily true. Some of it will be, but there's also Ngaruroro water that finds its way over there as well.
I understand that. I understand through all the work that David Reynolds has done that when there's high rainfall, that the Ngaruroro picks up. But on the whole, it's fair to say that the Tukituk Aquifer, until there's extreme weather conditions, takes precedent over the Ngaruroro Aquifer coming back to meet it. So, so let's say 90% of the time we're deriving our water from the Tukituk Aquifer.
Yep. Do you have any comments to make on that, Uwe, based on the...
In one of my figures I showed the recharge source and the Brookvale wells, they actually all have rain recharge signature. So they are not recharged from a river, which we interpret at that stage. The water is recharged in the area here in the Tukituki gravel fan, which is highly conductive. So it's the rainwater which is falling in this area of where the Tukituki river fan outcrops, and that's the water which we are drawing in from Brookvale wells.
I understand that, but it's fair to say that being an old riverbed, in exactly the same way as the old Waipawa riverbed, is now called the Papanui stream, which runs under and over. That was dammed in 1896 by Samuel Williams. I can't quite understand how an old riverbed is not a living and a flowable aquifer today. I understand, yes, it's recharged by rain, but can you categorically say that the water, we can see the rivers, they run out to sea, but do we really understand that they're not running along their old seabeds like they used to?
I don't quite understand the question.
Is the old Tukituk riverbed not a Tukituk aquifer that's flowing in its old course, as well as what we can see the Tukituk running out to sea? It could also be, we've got the Ngaruroro aquifer beneath it, and we know that I'm asking you the question, is the Tukituk aquifer is it an aquifer, or is it just a dry old riverbed that doesn't have any water in its in the components of gravel? Is it a living aquifer in the same way as a Ngaruroro is a flowing aquifer?
This might be the case. The results which I showed, these are wells only going down 20 or 25 meter deep. So further down, there might well be a Tukituki water which is lost from a Tukituki river. Do you want to answer this a bit more?
And in that case, sorry, Lawrence, I won't go on. So it's fair to say that we're deriving our municipal water from remnants of the Tukituk aquifer.
Do you want to answer that?
Yeah, we are. The geological material, definitely. The water itself doesn't necessarily have to come from the Tukituki River itself. But, yeah.
And I should just say that the bore that was identified where the water was come has functioned for 35 years without incident. One E. coli measurement in that whole time that's been recorded. So it's not as though the system, until very recently, hadn't worked. It had. So we can't explain the young water that we found in February of last year, that we got the test results in August. Some of that water was less than a month old. We can't explain that. But it is part of the work that's being done to try and understand what's happening in the aquifer more. Maury. I'll come to you, ma'am. I'll come to you. Yeah.
A question for John Begg. All over the aquifer there are different heights in hydraulic head. Is it possible that parts of the unconfined aquifer are sealed off from other parts?
Thanks very much, Maury, for the good question. I'm not a hydrogeologist, so I'm going to talk to you from the point of view of a very simple geologist. And the answer is yes, that the gravels aren't necessarily separated by something that won't conduct water, by fine-grained material. In other words, it won't conduct water, I guess. That's for the hydrologists. But sometimes they are and sometimes they aren't. And sometimes the pathways, if you like, of the gravel streams that were flowing down to the water's edge were circuitous, and they were in fine-grained materials. And so presumably those gravels can conduct water down that circuitous pathway. So everything depends on the separation from the surface. And I think it's fair to say that if you go right up to the big corner at Marakakao in the Ngāruaru, then it's very likely that the last glacial gravels, which are the main aquifer that we're talking about beneath the Heretaunga Plains, is actually in contact with the young gravels that have come down across them, across those gravels and across the top of the aquiclude in more recent times. Does that answer your question?
Yes. I'm just aware that all around the plains there are these sort of fingers of strata poking out into the aquifer. And out at Paki you can have a well down in one place and then you drill a well 5 steps to the left and you don't hit it. So you've got flowing water in sort of fingers in places?
I think so, yes.
But are there parts where the aquifer is actually sealed off from going anywhere else?
I think that's true, Maury, but I'll possibly pass you over to an expert.
Yeah, that's entirely possible. You can have lenses of water within the aquifer system, and it's definitely blind as you get out to the coast. It's pinched off by those clay layers near the coast, so it has to go out through the upper layers. We don't know much about the deeper system. That's what we think based on the pressures. The way to really tell, and especially in those localised areas, is to do that airborne survey that I talked about earlier, or do lots and lots and lots of drilling.
I'm just going to take a bit of poetic license to ask a question on behalf of you all, because I've always been told, and you put it on your graph, that actually the aquifer is a dynamic thing and it's constantly flowing out to sea, and that there's lots of water. And because people that would argue against water bottling or other types of uses would say that actually we shouldn't do it. But on the other side of that argument, people say, well, actually the water's going out to sea anyway. Why don't we create some value along the way? Now the answer is it going out to sea? And how much of it is going out to sea, you know, as the total volumes?
Yep. So no one knows exactly how much water is discharging offshore. We don't know exactly where it's going, but based on the modelling that we've done, I think it's around 3.5 cubic metres a second would be discharged offshore if there were no takes. It's probably about half that when you include the abstraction. So yep, definitely we're getting value from that water that would have otherwise discharged off to sea. Just make a point though, especially with relation to surface water, but also to groundwater, is that water that flows to sea isn't necessarily wasted. It adds value on the way for ecosystems in the case of surface water, and groundwater too. We don't know what value those, or if there even are submarine springs out there, but they're rumoured to be, and what value that adds to the marine system as well.
So we're saying up to half? Yeah. Yeah. So up to half, okay. Right, ma'am.
Sarah Gerard again. So I think we're at an important point of science, trying to work out what previously, back to the Tuki Aquifer, David and Brown in 1997 provided a comprehensive groundwater study for Hawke's Bay Regional Council. And in that study, it had the Tuki Aquifer. And it was recharged. It was a very small, shallow aquifer recharged by the Tuki River. And the bore 1 and 2 draw from that Tuki Aquifer. And bore 3, the Heretaunga Plains aquifer interconnects at that point, and it goes, the two are quite, they interconnect. So depending on how much irrigation is drawn, that sort of thing. So I'm curious why we're not discussing, yes, we've found new science, the Tuki Aquifer doesn't exist anymore, and this is what the result is. But we're not even addressing the Tuki Aquifer. And so when I listen to you, I think, why aren't they talking about it? It's exciting that you found this new science to tell us that it's no longer recharged by the Tuki River. That doesn't exist anymore. But instead, we're not getting a clear message, and I want a clear message. So I'm asking the scientists.
I'll let them answer, but I think in reality, we don't know enough yet to be able to say that. We are clear, you know, and if you want to counter me if I'm wrong, but we clearly, with this modelling, with the age testing, and with this flying around in a helicopter type testing, I'm not trying to belittle that, we will actually get a far better understanding of what's going on more than we know today.
But I'm sorry, all of the discussion right through the government inquiry has been about the Tamata Aquifer. Now, I'm not sure where that term comes from. I think it might be a more water management term. I'm not sure. What recharges the the Tamata Aquifer? I'm not sure where that term came from, because the groundwater study that is the most comprehensive science that we've got talks about the Tuki Aquifer. So I'm at a loss of.
Yeah, but I'm not sure the point you're trying to get to, because actually the inquiry found that the most likely source of the contamination was water getting into the Manga Territory stream and being sucked into a connection into that aquifer about 90 metres away. So whether we have a Tuki aquifer or we don't have a Tuki aquifer, it actually is not really germane to what the inquiry found.
But it's not, it's understanding the characteristics of that unique characteristics of that particular aquifer that may be important for us to move on and know what we're working with when we're talking about national recommendations. Have we got an aquifer that has got its own particular issues, and that we've got to learn from those particular issues and move on from it, find another aquifer? Or is it more that we got an aquifer issue throughout and we have to go and explore all the aquifers in New Zealand because of these issues?
Well, I think all this science will help that understanding. What I'm saying to you is there's a lot of stuff here we don't know, and we're trying to learn using the best science we can to understand it. And I'm not sure I can answer your question. You can try.
I don't know whether I can help you very much at all, Sarah. What I do is I look at the materials, and what I see when I slice up our model, that the drill hole logs tell me that in this place there's gravel at this elevation, and there's not gravel, there's fine-grained materials elsewhere. So I can slice through the thing, and I see these lumps of spatial lumps which are dominated by gravels, and so I'll call that a gravel. I'm happy to call that a gravel. I assume interconnection. Now, whether you call that an aquifer or not, I don't know that the water knows whether it's in the Tukituki aquifer or the Tamata or the Heretaunga Plains aquifer. I don't know that it knows, but the system is inherently, it's a whole group of pipes or tubes, if you like, that are kind of interconnected in some way or another and kind of separated in other ways. And whether you put names on the aquifers or not, I don't actually. So what I imagine, this is a simple geologist imagining what a groundwater scientist is trying to understand is what the flow of the water through these gravel systems is. And whether they're separated, they're all together, they're the groundwater system. And separation is probably local in most cases. Does that help?
Yes, yes, the groundwater flows are shown to be from the Tukituki River to the bores in that direction. So that's the science that I've picked up. So therefore I'm curious about, is there science now saying that there's no longer those flow paths from the Tukituki River to the bores? Is that the science? Is that what we're saying now?
I think if David Dravid were here today, he would be the first to acknowledge that his work, which I agree is a seriously outstanding piece of work, and probably the most comprehensive package of work that we have of the Heretaunga Plains, but if he was here today, he would be the first to say that that part of his reporting, this location here, there was a great deal of knowledge that we didn't have, and there's a lot of assumptions made in the work that he had there in terms of it being confined, whether the Tukituki gravels are exactly finished here or whatever, and the flow paths as well. As Lawrence said, the science is improving. We know a lot more now. John showed us some geological modelling that's the best we've got. There's also room for more science to be done there and understand it perfectly. And Uwe has also talked about the source of the water, and as he said before, or as Lawrence said before, the source of this event that happened was the Mangateri River 90 metres from the bore. It was, and whether we call it the Tukituki Aquifer or the Tamata Aquifer, as a scientist, I don't mind. I don't have any sort of qualms with what we call it, Aki. Sorry.
I'm going to stop there. Look, I've got people leaving. So these guys are going to stay. Yeah, no, these guys are going to stay for a minute. We're going to stop now because a number of people do need to go, but these people will be here. So I just want to thank you all for your time and your presentations. And there will be some time just shortly after if I ask you to stay. So these individuals can come up and ask the questions, and I'll now ask Nahiwi to close the day.
You want to sing a waiata, Aggie?
One comment about what is out to sea is that our old people used to tell us when the Heretaunga species, the longfin tuna, migrate from central Tonga, those fresh waters was to help them change their biology so they could immigrate and migrate upstream. And the same is on the outer. When they have to read females after 60 years in our water, have to return to Tonga to think the water is the blending of fresh and salt water which helps them to acclimatise and change their biology. There is a reason.
Kia ora, kia ora. Well, please give a round of hand for all the presenters today. And we start at 8:30 in the morning. So see you nice and fresh, bright-eyed, and we're off again. It's been a learning experience for everyone, I am sure. So people came with pre-ideas about what they knew. I'm sure that was opened up a lot of minds today. So without further ado, I'll just close it with a tohi from Ranginui to Papatuanuku, the tears of Ranginui coming down to Papatuanuku, hitting the water, going into the aquifer, out of the sea, and then haumia hui e taia ki. I o nui, i o ro, i o te mataho, i o taketake, i o wānanga, i o tiki tiki te rangi, papatua nuku, rangi nui, roi mata aroha, mai ngā tihi maunga, ki te moana, haumia, hui e, taia ki. See you all tomorrow morning.